Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we started our discussion on inverse Z transform and discussed two of the methods, power series expansion method and partial fraction expansion method. In today's lecture, we'll continue our discussion on contour integration method to obtain the inverse Z transform, and later we'll discuss causality and stability in terms of Z transform. So before we go into causality and stability, let us finish the third method of inverse Z transform, which is contour integration. Now we are redoing this because we discussed how to obtain the inverse Z transform while defining the Z transform in the earlier lecture. So we'll consider a formal relation expressing a sequence in terms of its Z transform for Z equals to R e to the power j omega. That is, x of z is Fourier transform of the sequence x of n multiplied by r to the power minus n. Now if we substitute z equals to r e to the power j omega, then it will be x of r e to the power j omega equals to Fourier transform of x of n r to the power minus n. For any value of r, so that z equals to r e to the power j omega is inside region of convergence. Applying inverse z transform on the equation 1, the inverse z transform on equation 1 will result x of n r to the power minus n. And on the left hand side, it will be an inverse Fourier, because by applying inverse Fourier to x of r e to the power j omega, will be obtaining the discrete time sequence x of n r to the power minus n. So sending r to the power minus n to the right hand side, x of n will be equals to r to the power plus n Fourier inverse of x of r e to the power j omega. Now using inverse Fourier transform expression, x of n will be equals to the right hand side. We can write it as r to the power n 1 by 2 pi integration over 2 pi x of r e to the power j omega multiplied by e to the power j omega n integration with respect to omega. Now combining r to the power n with an exponential e to the power j omega n, the integral can be rewritten as 1 divided by 2 pi integral over 2 pi x r e to the power j omega multiplied by r e to the power j omega to the power n. Now n has been taken common, integration with respect to omega, and we know that r e to the power j omega will be z in the z transform. So using that, x of n will be equals to 1 divided by 2 pi integration over 2 pi x of r e to the power j omega z to the power n integration with respect to omega. Now this means we can recover discrete time sequence x of n from its z transform, which is evaluated along a contour z equals to r e to the power j omega. Now in the region of convergence, where r is fixed and omega varying over a 2 pi interval, if z is equal to r e to the power j omega for fixed value of r, then by differentiating z, we can obtain dz equals to j r e to the power j omega d omega, which will be equals to j into z, because r e to the power j omega is z d omega, or d omega will be equals to dz divided by j into z. The integration in this equation 2 is over 2 pi interval in omega. It means z corresponds to one traversal around the circle of radius mod of z equals to r. So 2 can be rewritten as x of n equals to 1 divided by 2 pi j closed integral, because the z traverse on a circle, one circle, that is from minus pi to plus pi and plus pi to minus pi. X of z, z to the power n minus 1 integration with respect to Z, where the notation circle with a small arrow denotes integration around a counterclockwise closed circular contour centered at origin and with the radius r. Now this is the same expression we obtained while discussing the definition of Z transform. So this is the contour integration method. By x of z will be able to obtain or will be able to recover the discrete time sequence x of n. Now we'll be just discussing the concept of contour integration. Problems on contour integration is out of the scope of our syllabus. So we'll solve a problem on Z to obtain the inverse Z transform from the Z transform by using partial fraction expansion method and partial fraction method. Z transform is defined as x of z equals to z divided by 2z square minus 3z plus 1. Using partial fraction method, the region of convergence will be mod of z less than half, and by using power series expansion method, region of convergence mod of z will be greater than 1. So we'll do the first method, power series expansion method. X of z equals to z divided by 2z square minus 3z plus 1, where mod of z is greater than 1. So expressing this in the negative powers of z, x of z can be written as z inverse divided by 2 minus 3z inverse plus z to the power minus 2. Now by applying or by using long division method, we'll divide the numerator by denominator. So by applying long division method, the series that we'll obtain is half z to the power minus 1 plus 3 by 4 z to the power minus 2 plus 7 by 8 z to the power minus 3 plus 15 by 16 z to the power minus 4 and so on. This will be an infinite series. And the constants associated with each of these powers will be the sample in the discrete time sequence at that position. For example, there is no constant in this power series expansion. Therefore, the value associated with n equals to 0 will be 0. Next, half, 3 by 4, 7 by 8, 15 by 16 and so on. This is the discrete time sequence obtained as an inverse Z transform by applying power series expansion method. Now we'll be looking into partial fraction expansion method for the Z transform z divided by 2z square minus 3z plus 1. So according to the first step, we'll write x of z divided by z. So right hand side will be 1 divided by 2z square minus 3z plus 1. We'll factorize the denominator, 1 divided by 2z minus 1 and z minus 1. There are two poles. So there will be two residues, a divided by 2z minus 1 plus b divided by z minus 1. Value of a and b will be calculated. A equals to 2z minus 1 x of z divided by z, where z will be equals to half. Simplifying this, will get minus 2, a value as minus 2. And b will be equals to z minus 1 x of z divided by z, where z will be equals to 1. Simplifying this, will get b value as 1. Now using this in the z transform and sending z from the denominator to the numerator on the other side, x of z will be written as minus 2 of z divided by 2z minus half plus z divided by z minus 1. 2 in the numerator and denominator will cancel, so we'll remain with minus 1 multiplied by z divided by z minus half plus z divided by z minus 1. Or simplifying this and expressing it in the negative powers of z, x of z will be equals to 1 divided by 1 minus z inverse minus 1 divided by 1 minus half z inverse. So for the given region of convergence, the discrete time sequence x of n will be minus 1 to the power n u of minus n minus 1 minus 0.5 to the power n u of minus n minus 1. These are the three methods using which we can obtain the inverse Z transform. The next concept we'll be studying is causality and stability. Now this Z transform that we are studying plays a particularly important role in the analysis and representation of the discrete linear time invariant systems and signals. And from the convolution property, we know that output in the Z domain, y of z, will be product between the Z transform of the impulse response and Z transform of the input, which will be given by y of z equals to h of z multiplied by x of z, where x of z is the Z transform of the input signal x of n, y of z is the Z transform of the output signal y of n, and h of z is the Z transform of the impulse response h of n. And this h of z, which is the Z transform of the impulse response, is generally referred to as system function or transfer function of the system. Now this system function or transfer function is the system characterization in the Z domain. And if Z evaluated on the unit circle, then transfer function will be reduced to frequency response, because if Z transform is evaluated on the unit circle, then it will be Fourier transform. So for Z equals to 1, system function or transfer function will be reduced to frequency response, provided unit circle is in the region of convergence of the system function h of z. And we also know that if input to an linear time invariant system is complex exponential signal defined as z to the power n, then the output from linear time invariant system will be h of z, z to the power n. Therefore, z to the power n is an eigenfunction and h of z is the eigenvalue of the linear time invariant system. So with this knowledge, we'll try to study causality and stability with respect to Z transform. And by the definition that we studied in module 2, we know that a system is causal if the output of the system depends on present input, past input, and in some cases past outputs as well, but not on the future values of the input. And from the definition we studied in module 3, a linear time invariant system will be causal if its impulse response is 0 for negative values of n or for n less than 0. If n is less than 0 or impulse response is 0 for n less than 0, it means the impulse response have to be an right-sided sequence. And we know that the region of convergence of the system function h of z will be exterior of the circle in the z plane. So in general, for a right-sided impulse response, the region of convergence may or may not include infinity. Both possibilities are there because the region of convergence will be exterior to the circle. So this may include infinity. So the region of convergence may include infinity or may not include infinity. We'll have to verify that. For causal systems, the power series or the system function, which will be the Z transform of the impulse response, will be given as h of z equals to summation n equals to 0 to infinity h of n z to the power minus n. The lower limit in the summation is 0 because the system is causal, and for causal system impulse response will be 0 for n less than 0. So it will be starting from n equals to 0. So the lower limit is 0. Now this equation, this power series does not include any positive powers of z. For every iteration on n, the z power will be negative itself, and consequently the last value on the summation is infinity. Therefore, the region of convergence includes infinity. By this we can define the nature of causality for Z transform. A discrete linear time invariant system is causal if and only if the region of convergence of its system function is the exterior of a circle including infinity. So entire Z plane outside the circle, if it is region of convergence for a given Z transform, then discrete linear time invariant system will be causal. And if the system function h of z is rational, then for the system to be causal, the region of convergence must be outside the outermost pole, and infinity must be in the region of convergence. Equivalently, the limit of the system function as z tends to infinity must be finite. Now, this is equivalent to saying that numerator of the system function h of z should be having the degree no larger than the denominator when both are expressed in polynomials of z. Now, if we express h of z, the system function, as a ratio of two polynomials, then for linear time invariant system to be causal, the degree of the numerator polynomial should be less than the degree of the denominator polynomial. So combining the two conditions, we can define the causality of linear time invariant system in Z transform as a discrete linear time invariant system with rational system function h of z will be causal if and only if the first point, the region of convergence, is the exterior of the circle outside the outermost pole, and the system function h of z, when expressed as a ratio of polynomials in z, the order of the numerator cannot be greater than the order of the denominator. If these two conditions are satisfied, then discrete linear time invariant system will be causal. The second property we'll be studying is stability. Now, stability of a discrete linear time invariant system is equivalent to its impulse response being absolutely summable. That is the only condition on stability here. The impulse response of linear time invariant system has to be absolutely summable. If it is absolutely summable, then discrete linear time invariant system will be stable. Now, in this case, the Fourier transform of the impulse response h of n converges, and consequently the region of convergence of the system function must include the unit circle. Therefore, that absolute summability is defined as summation n minus infinity to plus infinity mod of h of n should be less than infinity. And we know that the system function is defined as h of z equals to summation n minus infinity to plus infinity h of n z to the power minus n. Now, taking magnitude on both of the sides, and we know that magnitude of the overall sum will be less than sum of the magnitudes of individual terms. Therefore, instead of equality sign, we'll use less than. Mod of h of z or magnitude of h of z will be less than summation n minus infinity to plus infinity magnitude of h of n z to the power minus n. And we know that the product of magnitude of the product will be equal to product of two individual magnitude terms. So using it, we'll write mod h of z less than summation n minus infinity to plus infinity mod of h of n multiplied by mod of z to the power minus n. Now, mod of z to the power minus n will be equals to 1 when evaluated on the unit circle. Therefore, mod of z to the power minus n equals to mod of z will be equals to 1. Using this result, mod of h of z less than summation n minus infinity to plus infinity mod of the impulse response h of n. Now, this has to be a finite value less than infinity when evaluated on the unit circle. Therefore, a linear time invariant system is stable if and only if the region of convergence of its system function h of z includes the unit circle, that is mod of z equals to 1. Now, the two properties, causality and stability, for any linear time invariant system, it is perfectly possible for system to be stable but not a causal one. However, if we focus on causal systems, stability can be easily checked by examining the locations of the poles. Specifically, for a causal system with rational system function, the region of convergence should be outside the outermost pole. For this region of convergence to include unit circle, all the poles of the system must be inside the unit circle, and that is possible only when all of the pole values are less than 1. Therefore, a causal linear time invariant system with rational system function h of z is stable if and only if all of the poles of the system function h of z lie inside the unit circle. That is, all the pole values must be having a smaller magnitude smaller than 1. All of the poles should be within the unit circle itself. So they must all have magnitude smaller than 1. So we'll consider an example to verify the causality and stability. A system is defined by the system function or the transfer function h of z equals to 1 divided by 1 minus half z inverse plus 1 divided by 1 minus 2 z inverse for region of convergence mod of z greater than 2. Now, is this system causal? The region of convergence for this system function is the exterior of the circle outside the outermost pole. There are two poles, one at z equals to half and another at z equals to 2. So the highest pole is 2 and the region of convergence is outside that outermost pole. And we know that the impulse response, because of this nature of the region of convergence, the impulse response is the right-sided sequence. Now, to determine if the system is causal, we'll just check the degree of the numerator polynomial and denominator polynomial when expressed as ratio of two polynomials. So, expressing h of z, the system function, as ratio of two polynomials, it will be 2 minus 5 by 2 z inverse divided by 1 minus half z inverse multiplied by 1 minus 2 z inverse. So simplifying this, it can be written as 2 z square minus 5 by 2 z divided by z square minus 5 by 2 z minus 1. Because the numerator polynomial and denominator polynomial degrees are same, that is 2, the highest power of z in numerator and denominator is 2. So the degree of both numerator and denominator is same or equal to 2. Therefore, the system is causal system. As a second example, we'll consider system defined as h of z equals to 1 divided by 1 minus a z inverse. Now, we said this is a causal system. Now, is it stable? Now, the system function has only one pole at z equals to a. For this system to be stable, all the poles must be inside the unit circle. That is, mod of a should be less than 1. Then only the following causal system will be stable, or else it will be an unstable system. I hope all of you understood the definition of causality and stability for a linear time invariant system with respect to Z transform. If you have any doubts, you can contact me. Thank you all.